Second before we distract from the speaker. Those of you that I send emails to know I sign myself as David A. And on this sim pretext, I'm going to introduce this afternoon's speaker, Bartek B.
Thank you very much. Thank you very much. I'm used to this kind of introduction. So I'm not going to read this lengthy title that I produced for the sake of this booklet. Let me say that everything that I'll be talking about is based on several joint papers with different configurations with François, with our colleague from INRIA, Paul Multaler, and with our younger colleague, actually PhD student, Omid Mirsadeghi, who is present in the audience. So I'm speaking under control. I'll be talking about ad hoc networks. So what is ad hoc network? For those who are not very familiar with this engineering terminology, this is a network made of nodes arbitrarily repartitioned in some region, say on the plane, and exchanging packets, either transmitting or receiving on a common frequency, and using intermediary retransmissions when some source is going to send something to a remote destination. So this is very vague, especially for the sake of this workshop. So let me make some precision. So ad hoc for me, what does it mean arbitrarily repartitioned? Nodes arbitrarily repartitioned, for the sake of this talk, means that given network nodes are modeled as an instance of a Poisson point process. So this is pretty precise, and just for this is a formality, I'm recalling what does it mean in Poisson point process of intensity lambda. For me, it will be always homogeneous Poisson point process. It means that it has Poisson number of points in any set A, and the number of points in disjoint sets are independent random variables. Another keyword, engineering keyword, that will appear in this talk is medium access control, MAC, nothing to do with the famous brand of computer manufacturer. And medium access, this is a part of the data communication protocol, which is very complicated, but there is one layer of it which is responsible of organizing simultaneous communications. If there are many nodes willing to communicate, there must be some mechanism saying, okay, these nodes can emit, others have to postpone their transmissions. And then in this talk, I'll be concentrated on the most simple, perhaps the most simple instance of such a medium access protocol, which is called Aloha, and actually means that if there are several nodes who are willing to emit some packet, actually each node independently flips a coin, and if heads, say, then it emits each node, this given node, and if tails, it postpones the transmission till the next time, say next time slot at this time is slotted. So okay, so this is something very quite often some natural mechanism for stochastic, especially for stochastic geometries, and where it is called thinning. Actually, Aloha medium access means nothing else than independent thinning with some given parameter p, the pattern of nodes who are willing to emit. So in my talk, medium access, very simple one, thinning. And actually this is the reason why we are looking at this simplest medium access mechanism, namely thinning, and not more complicated ones like CSMA in Patrick's talk, like message passing, some back pressure mechanism in other talks, because it's, well, I would say the only analytical treatable on the ground of stochastic geometry. And the reason for this is that thinning of a Poisson point process is known to reproduce Poisson point process with intensity just rescaled by the thinning. This retention probability, this probability that a given node is accepted for transmission. Okay, so Poisson plus this Aloha MAC thinning it gives some hope for the possibility of analytical treatment of what's going on in the network. And then I should say just at the very beginning that there is some important trade-off in that should be observed when tuning this parameter. So this is the main parameter. In this simple medium access mechanism, there is one parameter. There is this one, the probability of being accepted to transmit, and there is some important thing that should be looked at when correctly, in order to correctly tune this parameter. Namely, at one side we would like to have as many simultaneous communications as possible. So P should be, we tend to fix P close to 1. But then, given I am the node, that this is the kind of social imperative, social wish. And then, given I am the lucky guy, the one of these who are selected, I would like to be the only one, because then it improves my communications, it makes it more easy, more successful. So this, looking from this point of view, this individual point of view, I would tend to rather tune the parameter close to 0. So what's the good tuning of P? But we need some functionals which, when optimized, might give some insight on how to tune this parameter P. And partially I'll be talking about this. And then just I have to say why we cannot accept all the nodes willing to emit, because there is always the medium in which the communications take place has some limited capacity, either it's cable or, like in my talk, it's wireless medium. And it's some bandwidth, and it has usually some bounded capacity, meaning that not all the configurations of simultaneous communications are feasible simultaneously. And then the third part of my introduction, I have to say finally, what does that mean when configurations are successful, when some simultaneous communications are successful? And there is this principle that I'm going to look at throughout my talk, that in order for a given communication in presence of others to be successful, something that is called signal to interference, sometimes end noise ratio, has to be larger than some threshold. Meaning that I'm going to send something or talk to some given person. This person hears me with some given, receives my signal with some given power, and then the ratio between this received power and the ratio of the powers of all other signals, plus eventually some noise because of micro-ohms and things like that, this has to be above some threshold being related to the capacity of the communication, the throughput, and but anyway, there is something important, which is the ratio between power of the received signal to the power of the interference. And what is this interference? As I just said, is the sum of all unused, useless powers, disturbing powers received by a given receiver. So this is the third thing where stochastic geometry has a quite obvious and nice object ready to be used, namely the shot noise. The shot noise, it's nothing more than shot noise generated by some pattern of points, or point process phi. It's nothing more than just sum of some functions of two variables, the point of the point process and the given location on the plane, say. So this is, in my scenario, this will be always the sum of powers emitted by nodes in phi and powers being attenuated by this kind of function. I'll be more precise why it's of this form later on. So this was the third thing, this shot noise, quite nice object, well studied in stochastic geometry, and here is how it fits to this assumption on the pattern of points being Poisson. Namely, the crucial for all the analytical calculations, explicit calculations, the crucial formula was actually given during the previous talk, which is nothing else the Laplace transform on this shot noise that can be that can be obtained from the Laplace functional of the Poisson point process, which is known explicitly. And Sergei, who is now sitting here, he showed us. He was showing us several examples of the formulas of this type. Just one more thing, that this can be done also multidimensionally. So I can be interested in these shot noises at several locations, and then they are dependent random variables, but the joint Laplace transform is explicitly known. So somehow throughout the whole remaining part of my talk, I'll be working with Poisson repetition of nodes and shot noise interference being important to recognize which communications are successful and which are not. This is kind of stochastic geometry ingredient of my my setting, and then this engineering assumption that the medium access is aloha because it fits well to the stochastic geometry. Not because I would like to have it, but because I can. I cannot do better than this with respect to my program. So I have to say something about the related works, and actually there are quite recently quite many works in which wireless communication problems are treated on the ground on the stochastic geometry, say Poisson point process of nodes plus shot noise interference. So I will not be able to cite all the papers. I just please, these are the names in alphabetical order, by the way, of people who contributed probably the most to this whole area recently. But also I would like to mention that since the beginning and also recently, very many outstanding theoreticians of stochastic geometry, random graphs or percolation theory are interested in communication technology problems. Just to cite Gilbert, who probably started this kind of looking at the engineering problems. So here is the outline of the remaining part of the talk. There'll be three parts. I'll spend most of my time on talking on something that I call coverage probabilities. And coverage probabilities, that sounds familiar for stochastic geometers. It's not going to be exactly the same as because the models are not the same, but pretty related to what is usually called coverage probability in stochastic geometry. Then I'll slowly go to local delays. So I mean, basically what we'll do, we'll add to the static models studied by stochastic geometry, usually by stochastic geometry. I'll add time component. We'll be able to say something about the local delays, whatever it means in the networks. And then slowly I'll move to end-to-end delays, which is something related more to random graphs. And as almost necessary during this workshop, I will have my phase transition, and I have my percolation model. This time first passage percolation model. So hopefully by the end of the talk. Part 1. Coverage probabilities or successful transmission probabilities in some basic network model with aloha medium access. So here is the description of my basic model, the very basic model for which we are able to calculate very many things quite explicitly. We can study, optimize it, and which gives rise to more complicated models that I'll show you later on. So, as I said, I'll have a Poisson pattern of nodes xi, homogeneous Poisson pattern of nodes repetitioned on the plane with intensity lambda. And these points will be marked. So this will be a marked point process and independently marked point process. And here are the marks. So first this mark that says which node can transmit or not. So this is Bernoulli indicator of the thinning. EI, it's either 0 when node is not allowed to transmit and 1 when it is allowed to transmit. Everything is static in this model. So this is independent thinning of the independent Bernoulli random variables thinning the point process phi. As I said, the consequence of this independent thinning is that if I look at the points who are marked 1, namely emitters at a given time slot, this is a Poisson point process, again with the density lambda 1 equal lambda times pi. Okay, that's simple. There are receivers in this model, and that's why looking at these receivers, we discover why it's called bipolar model. So actually, we are going to assume that each node, each emitter, xy, its node in my network xi, is going to have its own dedicated receiver. I don't know exactly when, but in the radius r from this point. So this is kind of maybe strong assumption for people who are doing networking, because network is, I mean, every emitter has its receiver in the same distance. Okay, we have to live with it for some time. Later I'll show you some extensions, but all of this this assumption gives interesting results. So for those who like precise formalism, you might consider these yi as independent, again, marks, such that each mark is in the distance, it's a point of the plane, and the distance r to xi, and uniformly, for example, distributed on the ring. Further marks, these are multidimensional marks. So each node, that's quite important for wireless communications. So I'm node xi, and I have a vector of random variables fij, j running over all other nodes, and each a given variable fij. It describes the quality of the radio channel between me and the receiver of the node j. Okay. Why I need it random? Okay, if you don't like random, you can consider it fixed. But it is important for wireless communications to admit that the quality of channel varies on two different. Take emitter receiver and move it a little bit in space, just a little bit, a few meters, a few centimeters, and it varies in space as well as in time. So that's why people usually consider some these kind of variables. They call it fading in the channel. And then, as I said, in this simple model, these fading random variables will be these are completely independent across different receivers and across different nodes. So it's a matrix of IID random variables. Generic case, just a random variable with mu with mean 1 over mu, but there is one special case called by engineers Rayleigh fading and by mathematicians exponential fading, which assumes that this f is exponential. So it's not only for mathematical convenience, but there is some deep reason to look at this to be exponential in a special case. There is, I'm sorry, a third object that I have to introduce. I said that the quality of channel varies and depends. It's a random thing that depends from between 2 points. And I have to say that is, I mean, the way how I'm emitting a signal with some power, and this power is received at some distant point. Of course, it diminished. And here is the deterministic function Lx of the distance between emitter and receiver, which says how much my power is on average diminished. So actually, if I want to see what is the power received at some distance between emitter and receiver, it is emitted power C1 diminished by this deterministic function and multiplied by this random thing that I called fading. Okay, and then there is this often used simplified power law function, which is taken for L. Why OL? Why 3 and not 1 and 2? Because this function has polar the origin, so it's meaningless for small distances, and there are some ways to correct it that we call 1 and 2 in the book that some of you might already have seen on the table over there. So the third thing, I was already talking about that. What does it mean, successful communication? It means, as I said, that the ratio between received power at the given location y and power emitted by xi, and this is the formula for the received power, divided by the noise plus interference that I already explained to be a short noise created by emitters, actual nodes selected by medium access. So in phi 1, only those who are selected. This ratio, so useful signal received, noise plus interference, which is short noise larger than some threshold, and this is another parameter of the model. And this might be random variable, might be constant. For the time being, it's not It doesn't make any extra difficulty to consider it lambda variable. So we'll say that the communication from xi to yi is successful when this condition holds, when the ratio of received signal divided by power, by noise and interference larger than some threshold. Okay, so let's denote by working a little bit like in stochastic geometry. Let's denote by delta I indicator that this event holds for the node I, and this way we have produced another mark of the point xi. And with these new marks, obviously my point process enriched with this new sequence of marks, it's still stationary, so no problem, except that, now important thing, given everything else, so points and other marks, this sequence of marks is no longer IID sequence, as all the marks that I have assumed in the model. So what do stochastic geometers are interested first are in the distribution of the typical such mark, which is, so I mean they would call it like that, actually condition that a given node, a typical node is emitter, what's the probability of successful transmission of this node, and obviously this thing has interpretation that is somehow average number of nodes that can successfully communicate in some range B, and this average might be with expectation or under some ergodic assumption without this expectation with B growing. So for stochastic geometers and for the theory, it's just the probability of successful communication for the typical node. For those who see rather the one given repetition of nodes, this is a spatial average of fraction of nodes who successfully can communicate.
By now I thought that it's your construction, your model was translation invariant.
It is.
But why they are not IID? They are not independent, you say. So they're dependent, but they are not. Why they are?
No, because given repetition of node, given pattern of points, you have a large hole around you. I'm quite squeezed between other nodes. So obviously,
they're dependent. But why they are not?
Because my neighborhood is different than yours one. So they can't be independent.
What is it translation?
Okay, formally.
What is it in homogeneous space in your construction?
Fixed point process, okay, fixed, given repetition of nodes, okay? You have more interferers around you, have less. So why, given this situation constant, why should I have the same chance of successfully transmit successfully?
Why is unconstant? Or X is unconstant?
Given everything, fix everything, and then look, your chance.
Conditional distributions are different, but unconditionals are.
But unconditional distribution is nothing more than I mean, to define the format, this is distribution of the typical node. So, okay, so I think I'll skip the whole Palm formalism of this and then just proceed with the calculation of the probability that the typical node successfully transmits. Probability that the typical node, given it's selected, successfully transmits. So there's nothing more than probability that this channel condition, the quality of the channel condition for this node is larger than something, and this something being noise plus interference multiplied by the threshold and then by this attenuation function. This is just we have rewritten the ratio SINR, okay, signal to interference noise. And now you'll observe that here you have three independent random variables: this fading, noise, and interference created by other nodes, so independent of my quality of my channel. So having these three random variables independent, it should be not so difficult to calculate this probability, at least not hopeless. And indeed, especially it's easy when f is exponential, because then you can first calculate expectation with respect to probability that exponential is larger than something, and then average over I distribution of I and W. And this gives rise to the following formula, the first result, which gives you explicitly the probability of successful transmission by a typical node in my network, or my coverage probability, coverage being probability that my receiver is covered by me. And in particular, if the attenuation function also of this power law, this boils down to this extremely simple formula. And let me just point out that there is one important parameter here that somebody called spatial contention parameter, which depends on the attenuation function. I should say what this beta is. Beta says how fast the power is attenuated in the space. So in the free space model, beta should be 2. In real application, it's always larger than 2, and typically it's between 3 and 4. So in the countryside being more close to free space, nevertheless, even if you have always reflection from the ground, being close to 1, and large city, lot of buildings, typically larger. Smaller beta. Okay, there are linear models maybe. Okay, but I'm working on the plane. So the proof is simple. Actually, as I said, having observed that f is exponential, so first calculate probability, express the probability exponential, and the variable is larger than this something that we have seen before, is this one, and then taking expectation with respect a to w, observing that interference and noise are independent thing, you have immediately this product, and this being nothing else than this Laplace transform of the interference calculated at this argument, which is known in the closed formula. So we are done. Now there are trivial examples showing that it's useful, because, for example, this example shows how to tune the parameter. If you want to give some very vague guarantees on some level of successful transmission, but I'm not going to details. Okay, this was for exponential. So for some time we didn't know how to do it for general distribution function, in particular for deterministic. But okay, different than exponential. And that is because the only information we have, it's coded in the Laplace transform of the interference function. So okay, you can try to invert, do some fast Fourier transform to invert, but then formulas are not explicit. And then is this simple observation that if you restrict ourselves to the class of random variables which have square integrable density, then you have at your disposal the famous Poincare-Parseval theorem, which gives the isometry between density functions and the Laplace transforms, and this allows you to explain under the assumptions on square integrability of your fading, quality of channel, and shot noise, which can be again expressed in terms of the conditions on F, gives you this formula, which is okay more complicated than the previous one for the exponential one, fading, but still considerably less complicated than these contour integrals that you have when you want to use just the Fourier transform to calculate, to invert the formulas to invert the Fourier transform. Okay. Okay, bipolar means that network looks like a bunch of dipoles, or I don't know how to say in English, bipoles. I mean, two molecules bound together with a fixed distance. Emitter, receiver always together at a fixed distance, and this bunch of things distributed according to Poisson point process. So there is no variability between distance. I have my receiver and all my colleagues in the same situation. The geometry is simple. Every emitter has its receiver with a fixed distance. So it's kind of bunch of sticks of the distance are distributed according to Poisson point process on the plane. Okay, so having this more general result, we can study, for example, what is better, strong fading, higher variance of this channel quality, or smaller one. So there are examples. You just trace the curves for different variances and show, for example, that this fading, you find out that for the coverage probability, the fading is good. It helps for the communications on the larger distance, but it's rather bad for communications on the short distance. So maybe it's obvious, but we are able to produce evidence of this fact. And then you can always study other interesting quantities of interest, like for example, what is the mean progress of the packet? So my packet, if I'm sending something to my receiver, it progresses either distance r when the communication is successful, or nothing if it's not successful. So this mean packet progress is extremely simple.
Sorry, I cannot understand this thing. You have your Poisson field, you have these molecules, and how you choose these molecules?
The molecules are distributed according to Poisson point process. And
one end of this molecule.
Yes.
And the second one.
The second one, take the radius, take the angle uniformly distributed, for example, on the ring of radius r, and put your receiver there.
But you haven't any point, any Poisson point maybe in this.
No. These are extra points.
Extra.
Extra points. These are not the same points for this model. So I was not specific about this. These are extra points.
But you said that your points decide to be receiver or transmitter.
The only thing that, for me, the network is this Poisson point process. It's them who decide that we emit or not. And there are extra points, these satellites around them, which are the receivers.
So together they are not exponential.
No, they are not Poissonian. No, of course not. So mean progress, you might be interested in optimizing this mean packet progress in R, for example, and this can be done explicitly. I want to go to the case because my time is becoming shorter and shorter. But I mean, I think you are pretty convinced that having produced explicit formula for the coverage probability, we are able to evaluate to study to maximize this formula distance times the probability of successful communication distance r, and to find r for which it's maximized. And here are the explicit formulas. I don't want to discuss them. There are also interesting quantities, other interesting quantities of interest. For example, what is the average number of successful communications in a given region B? Okay, this we called density of successful transmissions, kind of social performance metric of the network. And this you can also optimize. Thanks to Campbell formula, as everybody knows, you can express it in this way. It's nothing more than the density of nodes times the probability a given node is selected by the medium access, and then probability of successful communication for this node. And then again, you can optimize, if you like, an R and P, and you can produce apparently interesting results, practical results. For example, saying that if the intensity of nodes is larger than some maximal intensity, some optimal intensity, you do not need any medium access mechanism. You just let all the nodes emit at the same time. But if it's larger than lambda is larger than some maximal one, then you, in order to optimize this density, you need to thin the nodes by the fraction which is given here. And again, this spatial contention parameter is inside the formula. There are other social or spatial performance metrics like spatial density of progress, spatial density of Shannon throughput, spatial density of transport. I don't have to even define them. Just let me show the conclusion for this simple model. So it's a very simple model. We are able to obtain closed expressions for the successful transmission probability, which is the first step when studying pertinent optimization problems for the network regarding the progress, the density of communications, and things like that. A better model is needed just because this model is kind of silly that there are these satellite receivers around the emitter, but I'll show how to do it in the next part. Before doing this, however, let me show you two simple extensions of this model where we still keep these satellite receivers, if you like, if you prefer the name, not bipolar, but satellite model. So one is the opportunistic thing. So what is ALOA doing? What is this medium access, this standard doing? Actually, it's not flips a coin, and then if it heads, it emits, otherwise it refrains from doing that. But if the channel is varying, there is something more smart that can be done. Namely, my coin should be somehow related to the quality of the channel. Anyway, these channels, we have assumed that they are IID. So why not making my coin dependent on the channel in such a way that I tend to be selected to emit whenever my channel is relatively good, and I should not be selected when my channel is not good. So this kind of mechanism that we call opportunistic ALOA, it's nothing else than the kind of ad hoc network variant of the protocol that is implemented nowadays everywhere in cellular networks. It's called HDR, high data rate, or HSDPA protocol in cellular networks. And the model of this protocol in this ad hoc setting would be nothing else than just making medium access this Bernoulli random variable saying whenever I'm selected to emit, make it dependent on fading, and for example, in such a way that if fading is larger than something, the something being or a constant or something that may be pre-selected randomly as well. And then actually it boils down to exactly the same model, except that now my EIs are not independent of FIs, but that is not a problem. You can calculate especially in some particular case when this level above which I'm going to transmit in some random fashion, and here is the formula, but it's maybe more interesting to look at the curves and look if you just apply this simple mechanism relating medium access decision to the quality of channel, that you can multiply by 2 the throughput, the spatial density of successful communications in the model. So that was one extension. Another one is non-slotted Aloha. So what is it about? Actually, in the Aloha, it's a very simple medium access mechanism, but I have assumed the version which is not the simplest one. I have assumed that even if nodes pick they write to emit independently, I have assumed that the time is slotted, that there's some universal clock, and all the simultaneous transmissions start at the same time and terminate at the same time. You don't need this assumption to implement Aloha. And actually, in the simplest scenario, every node emits a packet, then backs off for some exponential time and re-emits again, so on and so forth. So there is no synchronization between them. So we're able to produce to study a model which this phenomenon of asynchronous transmissions is present, and the reason for which I'm going to show it here is because we wanted to revisit this famous classical result saying that slotted Aloha outperforms by the number of 2 non-slotted one. This result being obtained for the model where there is no geometry, and where 2 simultaneous communications are always unsuccessful, which is not the case evidently in the wireless scenario when 2 communications are far apart. Maybe CNRS at both of them are still acceptable. So the model that we have, the simplest one that we can invent, is just instead of taking Poisson point process, this model requires space and time dimension. So instead of considering a point process on the plane, consider a Poisson rain, which is Poisson point process on space, or rather plane times time dimension, and look at the points of this point process in the 3 dimensions, plane times time. As points of this point process are just locations when the packets are emitted and times at which these events, these transmissions take place. Okay, you may think of this model as the network where nodes are born at location xi and ti just to emit one packet and disappear. It's kind of infinite population model, also started in the geometry in the setting without geometry. There's one thing you have to say what does it mean interference in this case, and if you assume some coding, if you take this interference, because interference it varies in time, then even during one transmission, because some other transmissions start or terminate. Take the average, and you're able to prove very nice formulas, especially this one, which is exactly the same as the previous one for slotted case, where now the spatial contention parameter is different, is given by this formula. Now, comparing this thing to the slotted, which is for non-slotted Aloha, to the case of slotted Aloha, you find out that this parameter is larger for non-slotted, meaning, because minus here, meaning that the probability of successful communication is indeed smaller than this for the slotted one. But actually, we can prove the result saying that the ratio between these two, it is the ratio between these 2 contention parameters which gives you the ratio between the throughputs of slotted and non-slotted Aloha. It's always between 1/2 and 1. Here is the curve. And interesting thing is that just looking what's happening on these 2 parts of my curve, when I'm more close to the free space propagation model, then both Aloha perform in the same manner. When the attenuation is very, very strong, then we are heading towards 1/2 foreseen by the discrete model. Okay, have only 20 minutes, but I said I'll spend much of my time on the first part and the second part. A new phase transition for local delays for ad hoc networks. So let me make first a resume on what is this about. So you know that communication networks usually have finite stability regions in temporal sense, meaning that the throughput is non-null only if the offered traffic is small enough. So in the stability region, so to say. And then this part is on kind of spatial stability of wired networks related to the way how the transmissions are dispersed in the space. So the setting is exactly as previously for my. So I have emitters located on the plane according to Poisson point process. Aloha is MAC. There is a CNR which identifies successful communications. And I'll be looking at the delays, how much time a given node needs to successfully transmit a packet. So I need a time dimension in this thing. And the result is of this sort. So looking microscopically on your network, you might find out that each particular network performs well. It has some finite mean time until the successful communication, so finite throughput. However, these finite local times, they vary from node to node, just because there are some people like Siri who are not in a kind of empty space, and others are quite stuffed in the clusters. And if you do space averaging of these individual delays, you find out that the spatial average is infinite. So what does that mean? To make a longer story shorter, it means that when you conceive a network, it might look, for a small size of the network, it might work. Given particular choice of parameters, the network might operate quite well, but your choice of parameters is not scaling with the size of the network. This instability would mean exactly this. So the model description is as follows: static Poisson points with some given intensity. Points are fixed; they do not move. There is a aloha, but now we consider different slots, not like just one before, but there are different slots. There's first, second, fourth, and so forth. And each node the nodes pick the right to transmit independently across the nodes and across the time slots, as aloha prescribes. Now for the fading, for this quality of channel, there are two natural cases to study. So either we just fix some quality of channel from the very beginning and they keep them during the time, fix them in an IAD manner at the very beginning and keep them for all time slots, or, so this I called slow fading, or at each time slot I'm resampling them. That is tremendous difference between these two mechanisms. One being called slow fading, the other fast fading. The same stuff for the noise. You might either, this external noise, either sample it once and keep it forever, or resample it at each time slot, which gives different models. So finally, I have promised you different receiver models, different than this satellite one. And here's the kind of ersatz one, intermediary between this simplest and maybe silly one, where actually there is my Poisson manet, this Poisson pattern of nodes, and there is another independent Poisson pattern of nodes called potential, or treated as potential receivers. And each node from this first one pattern of nodes, this first, each node from this pattern picks its receiver as a nearest neighbor from the other independent pattern. Okay,
so one receiver can have many connections.
Yeah, no. The nearest one is always one
Yes,
with probability.
for
Yes, but then is this signal to interference ratio, which if you have a situation like that, then probably neither communication is successful. That's fine. That's how it works in reality. If two emitters contact the same receiver, nobody is happy. But there is still some lack of reality in this model, that I have these two populations. One, they are true nodes, and there is this potential pattern of receivers. What does that mean in reality? In reality, you have just one pattern, Poisson pattern of nodes. So why sticking why assuming that there is one Poisson pattern of nodes, this one from the very beginning, and instead of satellite things or potential receivers, just assume that each node tries to contact its nearest neighbor in the same pattern. That's my true model, most difficult to study. And these two are kind of, we develop our skills looking at these models, but this is the one that we would like to look at. Again, there is a CNR, which now varies in time from slot to slot because at least fading, at least medium access parameters vary. And then there is indicator of successful communication at time slot n. And the main object that we are interested in now is the time a given node needs to successfully transmit a tagged packet. So say a given node I starts transmitting a tagged packet at time slot 1, and it waits until we are looking at the first moment that the node is authorized and transmission is successful. We call it local delay. Okay. Now there is a very important thing to understand what's going on here. So in my network, there are two kinds of random variables. One which are random in space, like repartition of nodes, and do not vary in time, like repartition in nodes, and my channel conditions, so fading and the slow fading scenario, or noise and slow fading scenario. And there are other who are resampled from slot to slot, okay, like medium access, like who can emit, who not, or fading and noise and the fast fading scenario. Okay, let's denote by S, if you like, sigma algebra generated by these random variables who are static, do not vary in time, okay. And having done this, there is a very, very basic observation that for a given node, given everything that is static, so given all these things that do not vary in time, the time and what this node is doing just Bernoulli schemes, Bernoulli trials, sorry, and this thing, because everything that is not static, it varies in an IID manner, so this local delay given everything that is static is nothing else that the time for the first success in the Bernoulli scheme, so it's geometric random variable with this parameter. This is probability of successful transmission given all the static elements of the network. So as we know, the mean of the geometric random variable is 1 over its parameter. However, as I said, it's given all the static elements, all the nodes, for example. So these conditional local delays will be different for Sergei and for me for the reason that I have explained already twice. So the problem is that in Poisson pattern of nodes, there'll be all kinds of extremal situations, like this being very small or this being very large. So how to study this variety of local delays? The first thing is to just study the average, the spatial average, large population average of these local delays, or in the language of stochastic geometry, local delay of the typical node. So okay, let's do this. As I said, given the static elements of the network, this is 1 over successful transmission probability, conditional, so this is 1 over this, so this was mean of the geometric random variable, which is okay, and then deconditioning of all the static elements, we obtain this, which is obviously by Jensen something larger than this thing, if you take all the expectations at the same level. And the whole story is about how far the left-hand side might be larger than the right-hand side. Obviously, this part, it's quite always, under very mild assumption, this is always non-zero, so this being finite. However, it's only smaller than than this expectation, and indeed, in quite many cases, this will be infinite while this is finite. Okay, to ensure you that it is really like that, let's consider two extremal scenarios. Very fast varying network. Everything is random. Even the locations of nodes are resampled in an IID manner from time to time. This is not my default assumption, but let's consider this. This is sometimes scenario considered in so-called delayed tolerant networks. So in this case, conditioning over static elements, there are no static elements, so conditioning over the trivial sigma algebra is just the expectation, which gives this. And this is P is fine, it's between 0 and 1, assuming that it's not 0. PC is the coverage probability I have evaluated before, so it's under my assumptions positive. This being positive, this being finite. So if everything is very rapidly, it's resampled in an IID manner in the network, this local delay, it's equal to 1 of the successful transmission probability times P, and then since this is always non-zero, this thing is always finite. On the other hand side, let's consider situation not realistic when nothing varies in time in the network. So everything is static. Even medium access, so all nodes peak, some nodes are authorized forever to emit, others are never authorized. Now this is unrealistic, but let's start at the extremal case. In this case, consider conditioning over static elements. What is static? Everything is static. If you have expectation given all the information, it's nothing more than nothing else than the random variable. So then the whole conditioning is at this expectation is this level. And look, it's enough that probability that E0, medium access, is smaller than 1. So with small probability that this might be 0, and this then is immediately infinite. So in this kind of static scenario, network is always unstable. So we should have understood by now that actually the spatial instability depends on, I would say, how much time variability averages out the spatial irregularities of the network. Or in other words, how much averaging is done at this level, at the temporal level, and how much left for the spatial averaging. More being done at this level, better for the spatial stability, for the local delay, for this expectation to be finite. Lesser done at this level, so more at this level, more difficult to get this infinite. So now, having observed these two extremal cases, you have to go through the whole zoo of the models, slow fading, fast fading, all these receivers model. But we have done that. It's tedious, but let me just conclude when this spatial instability might occur in the network. So in this simple model where there are satellite receivers, it can occur only if the noise is slow. The noise is not varying in time. And then you have phase transition, I have promised you. So you have this expectation of local delay finite for communication radius r small enough, or SINR threshold small enough, but there is some critical distance or critical threshold above which this expectation is infinite. And these two complicated models, where you're looking for your receivers as nearest neighbors and potential pattern of nodes or in the same pattern of nodes, this depends on, okay, let me put it this way. How potential receivers, so available receivers, outnumber the emitters. So it depends on how do you tune the parameter P. And then actually, and this holds even in the fast, if the noise is resampled in an IID manner and fading is resampled in a IID manner. So then you have this phase transition with respect to the tuning of your medium access. For small p, okay, it works well, but you just transgress some critical value of p and up, your network exhibits infinite spatial average of the local delay. Okay, I have to skip this. I have 5 minutes for the part 3 of my talk, where I promised you, but these things are related. Something on first passage percolation model, or end-to-end delays on long source destination routes. So it's for the first time now that we are interested in multi-hop routing. So there is this network that I have considered before. So I have Poisson pattern of nodes, only one given, no satellite things, no potential receiver, just one Poisson pattern of networks, of nodes, sorry. I consider slotted aloha, so each node time is slotted, and slot resamples its right to emit a packet. Okay, I'm considering only fast fading and fast noise scenario because these are two which are the most favorable for the spatial stability. There is no reason to consider worse cases. Actually, for the worst case, we'll have some negative results even under these assumptions. So, And again, successful transmission is decided by the value of the signal to interference noise ratio. So everything as before, Poisson, slotted ALOA, fast fading, fast noise, resampled in time in an IAD manner. However, there's one difficult, major difference between with respect to the previous model when I have studied local delays. Actually, I do not prescribe any receivers. But for any given node, I'm looking where are all potential, all receivers to which it could have tried and be successful. Okay? What does that mean exactly? This means that I'm not going to, because there are a variety of routing algorithms, which routing algorithm is something that decides where is really your nearest receiver, the next hop receiver, and how to route the packet from one node to the other. I'm not going to consider any practical one, any particular one. I'm going to look at all possible paths in space and time that I can use to send a packet from me to Marius, for example. Okay, all possible paths. I'm not prescribing any routing algorithm. I'm discovering all the possible space and time routes. So I'm constructing something that we call space-time SINR random graph. And what does this mean? A node of this graph consists of a location on the plane, being some node, and a given time slot. So this is three-dimensional. One component being two-dimensional. One component being point of the Poisson point process. The other being some slot in time. These are nodes. Where are edges in this graph? So there'll be directed edges because the graph will be oriented. So hence the graph will be oriented. And actually I'm putting an edge between node xi n, so point of the point process slot n, and another point of the point process j, and this slot just the next one. Whenever xi can successfully transmit packet to xj and then slot n. So whenever at time n there is a possibility to successfully communicate between x and from xi to xj. Or also I'm appending this graph by the edges, just staying at the same location, xi is the same, and just incrementing the time slot. So this graph, edges in this graph, these are actually, they show all the possible moves in my network at time t. So either from xi to some xj when communication is successful, or if it is not successful, or also the packet can stay, not be transmitted. In this case, at the next time slot, it's again in the location xi. This is my space-time graph. Yeah.
And these lines are strongly dependent.
Yes, of course. Okay. What we are going to do, you probably expect, we are trying to study shortest path on this graph. And what they do, they provide, of course, it's not a study of a given particular routing protocol, but instead it gives you intrinsic performance limitations, whatever practical routing mechanism. And the main performance characteristic is the following one. So I'm slowly heading towards first passage percolation model. Minimal number of hops to go from node O to node D, origin destination, divided by the Euclidean distance between O and D. And this ratio when O and D is going to infinity. So how much slots in my space-time graph and slots in my so many hops in my space-time graph and hops in my space-time graph, and nothing else than how many times I need, how many time slots, minimal number of time slots I need to go from O to D. Okay? And I'm excluding all queuing, so I'm always prioritary when, there's no queuing in this model. Here are two results. I have only two results. One is negative, one is positive. I'll tell you the last but one. This is the last but one transparency. So, if you assume your pattern of nodes, if you assume Poisson network, there is a negative result. Saying, sorry, I have to, I forgot to tell the classical, to recall you the classical setting, first passage percolation setting, this ratio, and this limit of this ratio is called time constant if exists. Okay? So I'll call this limit time constant, although in my models it's not always constant, sometimes it's random variable, but I don't have time to do it in detail. So, sorry, the first result, -1, for Poisson pattern of nodes. So only Poisson points. Then this time constant is infinite, principally due to large voids in the repartition of nodes. So the responsible characteristic of the point process is that can have arbitrarily large empty spaces. Not the clusters, it's the voids which are problematic.
The ratio in the formal transparency, is it a random variable?
Yes.
And it converges to constant.
Like in first passage percolation, the Holy Grail, somebody was talking Holy Grail, it was to prove that there is almost full convergence on this random variable to some constant called times constant.
This is infinite in this case.
Actually, it's not how we, okay, I'm not showing you precise formulations of the results, and I will not be able to show you proofs. So this is how I'm just telling the story. And the results you have to go to.
The distribution of this ratio just depends on the Euclidean distance between O and P.
Okay, to make it simple, instead of take the expectation and the expectation goes to infinity, if you like, for this result, for this negative result. So the times constant is infinite, meaning that whatever routing algorithms, when I'm going to send packets from some source to origin and being separated by larger and larger distance, the end-to-end delay is going to increase faster than the distance, so superlinearly. However, you can fix it, basically fixing the holes of the Poisson point process. For example, superposing Poisson point process with some regular point process, why not a regular grid which has guarantees that there are no voids. And in this case, the precisely this first passage percolation problem can be formulated and proved that the time constant is positive and finite. So there is end-to-end delay and this, okay.
You're right.
Finite, I'm very sorry. Okay, so as I said, I'm afraid I do not have enough time to precisely formulate the above results and present the elegant proofs. Please consult, for example, this paper or the book some of you might have already seen that is on the table in the hall. Thank you very much.
Okay, let me invite further questions or comments.
So in case of opportunistic aloha, the assumption is that channel state information is available at the transmitter.
Actually, if you are talking about the yes, of course, it requires at the beginning of time slot the emitter is able to sample the channel and to know what is the quality of the channel. Yes, right.
Do we have any more questions? Okay, we'll resume in half an hour. Thanks, Bartek, again.